So we'll have Sam telling us about rustling with bounded arithmetic. And yeah, this session is starting at 3:08 because I want to thank Russell for having me show up to another wonderful semester at Simons, where I learned to start everything on Berkeley time. Thank you, Sam.
Thank you. Want to thank Russell for having a birthday and letting us celebrate it, and thank the organizers for inviting me to speak. And so anyway, yeah, logicians do that, right? Okay, so I'm going to talk about constant depth proofs and bounded arithmetic, and I had a moment of panic earlier when Tony gave her talk that she was going to cover all my topics, but fortunately she moved on to other things, so I get to talk about this. And the other part here is the and bounded arithmetic, which is something I've worked on for many years, but it's very closely connected to constant depth proofs. Most of the talk will actually talk about constant depth proofs, but in fact, a lot of it comes from arithmetic. So just as a very quick background here, propositional logic means logic over variables that range over true false values. We'll use connectives and or not to form formulas. And a propositional proof, of course, is a syntactic object establishing the validity of a formula, or a syntactic object refuting a formula being satisfiable, right? And so very quickly, I think everyone knows this, but let me say it very quickly here. Why study propositional logic? On the theoretical side, there's very close connections to the PNP, or the NP co-NP problem, I should really say, the so-called Cook's program, towards approaching the P versus NP problem. On the practical side, SAT solvers are very widely used, unexpectedly efficient in many situations as proof systems, and they're also the basis for first order logic systems as other similar systems. So understanding what makes an efficient propositional proof system is certainly an important issue. Having said that, my talk is going to focus on the theory side. So the simplest propositional proof system that's widely used, well, maybe not quite true, is resolution, or some fragments found from conflict-driven clause learning. This is the basis for most SAT solvers, not by no means all, but for most of the successful SAT solvers. Lines in a resolution proof are clauses. So that means disjunctions of literals. A literal is a variable or a negated variable. So the clause P1, P2 bar, P7, P11, P15 bar just means the or of those things, P1 or not P2 or etc. Right? Or you can think of it as an implication. P7 and P15 implies P1 or 7 or 11. It's all mean the same things. Writing them in clause form, we're sort of thinking of a one-sided Tate-style calculus, as the logicians would say, and writing it in implication form, we're thinking of the sequent calculus. I'm going to stick with the Tate-style framework here. Resolution rule, everyone knows, I guess, C or from a clause C or P and a clause D or not P, we can infer the clause C or D, and this is our only rule of inference. I'm writing here or for unions of sets of literals, I guess. This is a depth zero proof system in the terminology of this talk. So what this means is that the formulas appearing in these clauses are literals, which are formulas of depth zero. So thinking of alternating ands and ors to level 0, right? Okay. So we can now extend this to depth K formulas, and this will take us up to essentially what's known as AC0 Frege. I think Tony talked about this, right? So depth K formulas are inductively defined by starting with literals as depth 0 formulas, and then forming, if you take a disjunction of depth K formulas or a conjunction of depth K formulas, you get a depth K plus 1 formula. And we'll measure sizes of formulas and sizes of proofs in terms of the number of symbols that are in the proofs. And depth K proof is one in which each line is a quote clause. I don't mean really a clause now, I mean a set of depth K formulas. So it's meaning the disjunction of a finite set of formulas of depth at most K. For the record here, proofs are DAG-like. I'm not going to get too much into technical details in the talk, but there's an exponential difference potentially in the size of proofs between DAG-like and tree-like proofs and so on. Or actually, I guess that's true, but I want to say something different. Going from depth K to depth K plus 1, you can take depth K plus 1 tree-like proofs and convert them to depth K DAG-like proofs and vice versa with polynomial size blow-ups. Okay. So, but I'm going to do DAG-like proofs here. The rules of inference then are, I called it cut now, but it looks identical to resolution from C or E, and from D or the negation of E, you can infer C or D. And by E bar, what I mean is take the E is a and of ors of ands of ors of literals, and just use a Morgan's laws to convert it into the negative formula, also depth K. And we have rules for, now that we've got ors and ands in the language, we have an or introduction rule and an and introduction rule. One advantage of the Tate style systems is we don't need to worry about the elimination. Those are just feel free to ask questions, by the way, during the talk. I probably have too much to say, so it doesn't matter if I get questions or not. Okay. Yeah, okay. On that note, okay. So for example, I think again, most people know this, right? But let me say it in case you don't. The pigeonhole principle clauses are clauses expressing the pigeonhole principle that there's no one-to-one map from n plus 1 pigeons into n holes. So we have variables xij, which are intended to mean that pigeon I flies to hole j. And so we'll let I range from 1 to n plus 1 with n plus 1 pigeons, and j range from 1 to n with n holes. And the pigeonhole principle sub n then is the following unsatisfiable set of clauses. We take for each fixed I, there's a clause that says pi1 or pi2 or ... up through pin. So each pigeon goes to at least one hole j. And then for each hole j and each distinct pair of pigeons I and I prime, either pigeon I doesn't go to hole j or pigeon I prime doesn't go to j. And as Tony did mention earlier, Hawken in 86, you said 88, I could have a read. Okay. It's a reverse auction to see who can pay the least. So Hawken somewhere in the 80s proved that any resolution refutation, which is the depth zero proof in my terminology in this talk, requires exponential size 2 to the n of the epsilon, right? And there is a long history of improved results for resolution lower bounds that I'm going to totally pass over in this talk, right? But Hawken was the first one. Okay. So that's great. Now back to depth K. Surprisingly, perhaps, depth K proofs were first discussed within the framework of bounded arithmetic. It wasn't the computer scientists who thought, hey, let's do proofs with depth K formulas, or let's talk about proofs of depth K formulas. It was in bounded arithmetic, I think the idea first came up. Harris and Wilkie in 1985 talked about this theory of bounded arithmetic I delta naught, and proved the theorem, which I'll come to in a little more detail in just a moment, that if I delta naught proves the first order pigeonhole principle, then there are, I'll say parentheses, constant depth proofs of the pigeonhole principle in propositional logic, or constant depth refutations of negation of the pigeonhole principle. I put the constant depth in parentheses because they didn't mention that they were constant depth. Their instruction just gave constant depth. And everyone who read their paper immediately realized this and filled in the words constant depth. Right, okay. So I delta naught was introduced by Rohi Parikh in 1971 to formalize the linear time hierarchy. They wanted to do a logic for linear time hierarchy, so alternating, constant alternation, linear time. He had variables ranging over non-negative integers, used the standard symbols of piano arithmetic, 0 successor, plus times, and he may have used less than, but I prefer less than or equal to. And bounded quantifiers, which I treat as syntactic objects for all x bounded by some term t, or exists x less than or equal to t, and then induction on only these bounded formulas. Bounded formulas being formulas that only have bounded quantifiers. And you can see that any delta naught formula, bounded formula, expresses a property in the linear time hierarchy. This was done in a paper of Lipton and someone else. I should have looked it up. The only catch really is that multiplication is not in linear time, as far as we know. So you just have to show it's in the linear time hierarchy. And then, so they express exactly linear time hierarchy properties. And also under the Paris-Wilkie translation, they correspond to families of constant depth polynomial size formulas. So what's the Paris-Wilkie translation? I probably should have made that blue. So make it blue. Okay. Okay. So Paris-Wilkie translation translates bounded formula. Now here we allow the bounded formula to include an uninterpreted predicate symbol alpha, like a second order object. It's like, think of it as an oracle. Okay. It translates it to a family of constant depth propositional formulas. So let me just give this by example. The pigeonhole principle in first order logic is the true statement that if for every x less than or equal to z plus 1, there's a y less than or equal to z, such that alpha x y holds, then there's a v less than z plus 1, another u less than z plus 1, and a y less than or equal to z, such that alpha u z and alpha v z both hold, right? So the hypothesis is that the function is a one-to-one function from z plus 1 to z, maybe it's z plus 2 to z plus 1, and the conclusion is that there's a collision, right? So let's rewrite this by, that's A implies B, so let's write that as not A and not B. And so here I've got the function is total, and the function does not have collisions here, written as a for all exists in a for all form. And then the Paris-Wilkie translation is just the clauses that says, well, what we had before. Oops, did I start? I didn't erase anything. There's the alpha xi turns to pij's. Think of the I as being a value of alpha xy turns to pij's. Think of I as being the value of x and j as being the value of y. And the not alpha uz or not alpha vz turns into not pij or not pi prime j. Right? What happened to for alls? Where did they go? They vanished. Why did they vanish? They became ands, and then they became separate clauses, right? So we're proving a refutation from a set of clauses. So I mean, all the clauses are true at once, that's their and, right? And that's the Paris-Wilkie translation. Great place for a question, by the way. Uh-oh, parentheses. Oh, which parentheses?
Like anyways, it's clear to me. I just wasn't sure if it was the other. So you're really saying like for every I, it has to map to some J.
So let's see. I've got here the subscript I means the set containing all these clauses. Union,
yeah.
The set containing.
Oh, okay, you're thinking of this clauses, right? I forgot.
Right. Yeah.
The conjunction. Yeah.
Yeah. Okay.
Union. I thought it was an or. Now I get it.
That's a union. Yeah, that's a union here. I'll make it a union. Okay. Okay. My files weren't slides may not quite perfect, but okay. Yeah.
So should the z's in that predicate be y?
Maybe.
Or did I?
Uh-oh, yeah, you're right. Look at that, man.
Like alpha u y alpha v. Sorry, I'm just parse it.
There. Okay. So, thank you. Yes. Very good. Yeah.
And Sam, can you say a little bit about, okay, the universal quantifier over X went to N? Like, how do you decide when you turn a quantifier into the sequence of formulas for different N's versus absorbing it into the formula like this?
Question is how to, yeah. So basically the outermost for alls turn into ands that break into separate clauses. If I had I could have a higher depth first order formula, and then it would turn into a higher depth translated formula. But I'm really interested in formulas that translate to sets of clauses in this talk. Good. Thanks for the questions. So the big theorem from Paris and Wilkie, among others, I guess, maybe it's more than one, is if a delta naught formula, whoops, the zero is in the wrong place. If a delta naught formula is provable in I delta naught, then it's Paris-Wilke translation, which is sometimes done with these double bracket signs. Is a set of unsatisfiable clauses which have polynomial size depth k refutations for some fixed k. And the point being that the I delta naught formula has in it formulas of some, it's a finite proof, so it's got finitely many formulas. So there's some upper bound k on the alternations of quantifiers. You translate the lines in the proof to propositional formulas. You translate the induction axioms to long strings of cuts, and you put it together and you get a propositional proof that's polynomial size. And so Paris-Wilke Woods, I was going to look up the year and didn't fit it in there. That's why it's a blank space there. The weak pigeonhole principle, which just says you can't have a one-to-one mapping from two n pigeons into n holes. It's provable in I delta naught plus omega 1, also known as the theory T2. And omega 1 is the axiom that gives you polynomial growth rates as the totality of the function x to the log x. Lets you get any polynomial growth rate function. So unlike I delta naught, which corresponded to the linear time hierarchy, I delta naught plus omega 1 would correspond to the polynomial time hierarchy. And the T2 is the union of theories I worked with later in my thesis, where I'll name them later on, that picked out theories that correspond to individual levels of the polynomial time hierarchy. Omega 1 is smash. And there's a whole hierarchy of omega sub k things. Okay. PQR, P is piano arithmetic, R is Robinson's theory, Q is also Robinson's theory. Okay, right. So, it was like it makes a V shape. P, Q, R, S, T. It's a V shape. Theories are getting stronger. So these were the famous theories. Well, P, of course, is piano arithmetic, and RS was from the book Mostovsky, Robinson, and Tarski, where they proved these really strong forms of the second incompleteness theorem. Really strong forms of the first incompleteness theorem. RSUV, the RSUV isomorphism. So see, then people backtrack from S, and there's an R theory that's then giving us a weaker induction.
So that's not the R that led you to S.
Turn it up and then back down to a different R. Okay, and the RSUV isomorphism. Okay, yeah, pretty bad naming, I guess, actually. So Paris-Wilke Woods used this theorem to prove that I delta naught plus omega 1 proves the existence of infinitely many primes. They exploited Sylvester's theorem to say that if there weren't infinitely many primes, then there'd be an injective mapping from a large set into a smaller set with a factor 2 difference in the large. So I delta naught plus omega 1 could prove the existence of arbitrary large primes. Still open whether this is provable without the omega 1 function. So as a corollary, but where I want to go in this talk is as a corollary, the two end-to-end pigeonhole principles have quasi-polynomial size, constant depth, oppositional proofs. Quasi-polynomial because now the omega 1 function is present. With I delta naught, if it were provable I delta naught, it would have polynomial size proofs. So here's the same theorem again. You don't have to read that. It's exactly identical. The thing in the green is the same as before. But the bottom part is Itai. Now the plot gets really interesting. Well, it was already extremely interesting. Now it gets doubly interesting. Itai showed, he proved that any non-standard model of I delta naught can be augmented to form a model in which the pigeonhole principle fails. And therefore, the pigeonhole principle clauses do not have polynomial size constant depth proofs. Now you may have noticed this is the converse of the theorem in the green, right? So it says, if something's provable in I delta naught, then it has constant depth proofs, right? This is saying things are not provable and therefore don't have constant depth proofs. The point was Itai's construction was general enough that you could take an object, if there were constant depth propositional proofs, the pigeonhole principle, you could encode it in a non-standard model, and then use in that non-standard model, still get a contradiction of the pigeonhole principle, and that would be a contradiction. So basically, he reversed direction of the theorem by the fact his construction is so good. little mini history here. Itai's first version didn't have the therefore part. He sent out a preprint with this theorem, but without the conclusion. And I wrote back to him. I don't remember if it was paper or email. It's very early days. And I think other people also pointed it out to him that, hey, you can also get this corollary for free. So he added it to the real version of the paper. I don't think I was the only one to mention this to him. This proof was very non-constructive. All sorts of, Oliver Corton gave a really nice presentation a few weeks ago at the Simons Institute. Very non-constructive, but this was a challenge to people like Tony, for instance, and others in the audience. She and her co-authors, Stephen Beltoni and Alistair Urquhart, were able to dig into this and give n to the log apply d+1 many times to n lower bound, which is super polynomial, on the size of constant depth proofs, depth d proofs of the pigeonhole principles. Okay. And I don't know, I've never actually pieced together whether this is actually Itai's construction or you had to do something else even more constructive than his. I feel like you had to really dig into the proof to get this out. Sure, it was not at all easy, right? What? He just used compactness, yes, so which of course is very non-constructive, right? But you know, this was, people were just getting started, so everyone goes, wow, look at this. And so two groups of people, the first group was Tony and Paul and Russell, and a separate group, Krychek, Quidlock, and Woods, who really concurrently, I guess that's a 90, that may be a 5 there where you can't read it, but they were done at almost identical times, gave exponential lower bounds. So fixed d, there's 2 to the n to the 6 to the minus d plus a constant as a lower bound on the size of depth d proofs for the pigeonhole principle. This is the n+1 to n pigeonhole principle, of course. And then you notice long, so 93 to 23 is a pretty long time. It's not for lack of trying. Eventually, Johann Hastad, in a preprint, as Paul mentioned in his talk, that came out just last month, or beginning of last month, it improved this size bounds to 2 to the n to the 1 over 2d minus 1, much better exponential lower bound. Right? Okay. And there was a series of papers before that I've named them here, Tony and others, on who started with Sighton principles, and these sort of improved up to this result. Right? These results depend on switching lemmas. So what's a switching lemma? And many of you know this. Switching lemma does the following. You take a depth d proof of the pigeonhole principle on n pigeons. That's an n there. And you set the values to many of the variables, okay, by, say, partially assigning pigeons to holes. You obtain a smaller instance, PHP M, right? And this is the magical part, is you reduce the depth of the formulas by 1 in the proof. So this is, you know, really an amazing construction, really. I guess the first one goes back to Hastad in about 85, although maybe the construction by Yale before that anticipated it, and Zipser maybe also a little bit. Yeah, first X, yeah, good. Yeah, first X. Yeah, okay, yeah, first X Zipser, and then Yao, and then was there Itai? There, Itai's. Yeah. So all these things were leading into the switching lemmas. And so if you know the traditional switching lemma, which probably most of you know switching lemmas is what you know, it's a pretty hard proof, but not that bad with the modern versions with that Sasha Razborov gave and Paul has explicated are not too hard to follow, right? But the newer proofs use these grid-based switching lemmas. So, and Hastad's new proof does as well, right? So so Hastad works in the following setup. You've got a chessboard with black and white squares, as I've drawn as black and blue, because I didn't really want to make white dots in these slides. And so it's size n by n, where n is odd. So there's, in this case, there's one more black square than blue square, black vertex than blue vertex. And we posit, for the sake of a contradiction, that every grid point is paired with one of its up to 4 neighboring grid points. Okay. So this gives a mapping. In particular, every black vertex is paired with a blue vertex. And the pairing is a bipartite pairing. I probably should have written that on the slides. So this is impossible because there's one more black vertex than blue vertex. And I started to fill this in with red lines. You can see the little red lines here, right? But I didn't want to get all the way because I would have eventually backed myself into a corner, right? So I just didn't want to show that. Well, this is a sparse version of the pigeonhole principle because unlike every pigeonhole pigeon going to any of the possible holes, every pigeon can go to only 4 of the holes. And it's already known lower bounds on proofs of the sparse pigeonhole principle from, oh boy, Ben-Sasson and Vigorson and somebody else. Or just the two? Just the two, okay. So Ben-Sasson and Vigorson already knew that. They took a random assignment of pigeons to a constant number of holes. But this is a very concrete version of a sparse pigeonhole principle. We just looked at this. And he then hits this with a switching lemma. And a switching lemma then is basically the following thing. I've got a picture, which is probably what you should look at. Sorry for being so bad artistically here. You take the square grid vertex. This is this big black thing here, right? You divide it into mini squares. These are these blue things here. You pick a random point on the first part of the diagonal of each blue mini square. And say like these are purple, but it's hard to see the color purple, I think, with these projectors, right? And you pick, this is going to be a new vertex. And now between each adjacent square, you pick some path between the vertices in that adjacent square. And that's going to hold a matching of edges going along that path. And, and basically you're saying that paths come in 2 types. Either they correspond to a edge between those not being present or being present. And you then take this big square that you started with, and now you have a new square on the purple vertices, and it's a smaller instance of the pigeonhole principle. Nice construction. And the same constructions were used earlier for sight principles. I mean, this is very similar in spirit to the kind of things that Tony and Bert are. One thing that comes up, I think it may be the first time in these proofs, but Tony can correct me. Substitutions now are no longer just projections. So you're no longer just replacing variables by constants like in the original switching lemma or by other literals. You're now replacing them by small size formulas as well. Okay, so Tony doesn't have a mic, but it was first in the earlier paper.
That was using projections. That was using projections. So yes. Yeah,
okay. So this may be the first time it's actually used this way. So we're starting to push the applicability or the tools used for the switching lemma. It's a pretty small, they're really small formulas. I'm really talking like size 3 or something like that. But we're now getting a little bit beyond just projections. So as a corollary, then immediately just by plugging into the lower bounds, that 2 to the n to the 1 over 2d lower bound, polynomial size proofs of the pigeonhole principle require depth omega log n over log n. Right. So we get a lower bound on the depth of polynomial size proofs of the pigeonhole principle. So a couple options. First of all, this corresponds, go back to the Hastad switching lemma of 85 or whatever year it was, right? That's the correct lower bound for polynomial size formulas defining parity for exactly the same reasons, right? The other comment is this is actually an optimal on the depth because I had proved 86 that the pigeonhole principle has proofs of depth order log n counting depth, however, based on fan-in 2 gates, right? So you can convert fan-in 2 gates to unbounded fan-in, but now dividing the depth by log or by log of the depth, I should say, right? And this is and then the usual construction works there. A fact that was first pointed out by, I think, Tony and one of your co-authors in a paper. Okay, we don't know, somewhere. It's folklore, okay. The first place I saw it in print, I think, was one of Tony's papers. So that's sort of brings together a lot here. I want to come back to this point in a minute. I see I'm running a little bit on time, but we did start late, didn't we? Yeah, okay. So now I want to set aside pigeonhole principle and constant depth and come back to an open question that's still open, right? What about separating depth D proofs from depth D plus 1? Right? So are there unsatisfiable, this is open, are there unsatisfiable sets of clauses of depth 0, right, that have polynomial size depth D plus 1 reputations, but require exponential size depth D reputations? I would consider this one of the most tantalizing open questions that's been now forgotten in proof complexity, because we know that depth D plus 1 is more expressive than depth D. We just don't know whether you can use it to prove more. Okay, everyone's looking quizzically like I'm saying something wrong, so if I am, correct me. I'll keep going, then you can say at the end. Okay, there's two things we know in this answer. First of all, there are sets of depth D formulas that have this property. They've got short proofs using depth D plus 1 formulas that require exponential size proofs using depth D. And this is basically, you take the pigeonhole principle and compose it with Sipserizing functions, get a pigeonhole principle on Sipser functions. So Sipser functions is what Hastad used to separate expressivity, depth D plus 1 from depth D. You see 0 circuits. Right? These are these little canonical and/or trees. Right? Okay. So that's great, but we'd really like to know something about depth D. And now, the best we do know is due to Russell and Jan Krajicek from 2002. So there, if you fix a D, there is an epsilon such that there's unsatisfiable sets of depth 0 clauses that have size M refutations of depth D plus 1, require size M to the log M to the epsilon refutations of depth D. So we get something super polynomial separation, but no better. And we really want exponential. And, from the logician point of view, I think of quasi-polynomial as the same as polynomial. That's what Hastad would give you. Yeah, Hastad, I guess, well, your first lower bounds gave that kind of thing, right? Oh, what Hastad would give you for what? No, the 2023 result, I don't think gives this. No, I don't think the 2023 result gives any improvement to the separation of depth D to depth D plus 1. Plus, we're missing upper bounds. To use the 2023 result to separate depth D to depth D plus 1, you also need upper bounds that match lower bounds, which we don't really have. I don't think. Maybe we do. I was racking my brain the last 2 days. I couldn't think of them. I missed them. Let me know. I'll come back to this in the talk. So the thing about this paper, now Russell might not recognize this theorem because he didn't state this theorem in the paper. What he's the second one you stated, the first one you didn't state.
No, but I think that's what we just, okay.
Maybe it's what you discussed, but it's not what's in the paper.
Because Jan wrote the paper.
Jan wrote the paper.
But basically this is like a half-hour conversation, just saying, well, why don't you just use the pigeonhole principle and water it down to polylog size? And he said, oh yeah, that works.
So the history, so this is Russell's side, then, which is great to get. They proved the first theorem, and Jan's side is they proved the second theorem.
Okay.
The second theorem on the page, and the second theorem is more uniform, right? So it is stated for fragments Ti2 of bounded arithmetic, and Ti2 is like I delta naught, but first of all, we've got the omega 1 thing, the smash function, which gives us polynomial growth rate. And secondly, we restrict induction to formulas from the ith level of the hierarchy. And now the Paris-Wilke theorem applies to Ti2. And I should say this on the next slide. The Paris-Wilke, I'll show you this again too. The Paris-Wilke theorem applies to Ti2, but gives you depth I minus 1.5 propositional proofs. Let me come back to that in a moment. Okay. So, but basically they stated for Ti2 that Ti plus 1, 2 of alpha is not conservative over Ti2. In other words, these low complexity formulas for all sigma B2 of alphas, they stated it. There's some things that are provable in Ti plus 1, 2, they're not provable in Ti2. Now, okay, so now the history gets a little convoluted. At some point I was looking back, I think some point, I mean, I looked at this paper, it was a nice little paper, and then set aside, just a couple of years ago, I looked at it again, I was thinking, well, why didn't they state the thing about separating depth D from depth D plus 1? Because I knew it followed from it. So I wrote to Jan, he said, oh yeah, Neil Toppin has pointed this out. And he put it in his new book on proof complexity. One of the chapters gives explicitly this separation. Okay. And so basically the idea of the proof is here, it's the bottom of this slide. Right, you take the exponential lower bounds on proofs, the pigeonhole principle, either the original forms due to sorry, that's the wrong initials, right? EBI, right? Yeah, okay. And on the proofs, and then you combine this with an old result of Paris and Wilkie, that the pigeonhole principle for on log n to the k many pigeons for fixed value k, but letting n vary, has polynomial size constant depth proofs because it's provable in I delta naught. So they show it's provable I delta naught, therefore it has constant depth. Positional proofs, constant depth. Positional proofs. And the theory TI2 is just what I just said a second ago. I won't say it again. It's on the slides. You can see them online afterwards if you want to. But basically, it's we'll just say it again. Proofs in TI2, the Paris-Wilkie translation gives you constant depth proofs of depth I minus 1/2. What does the 1/2 mean? So if something has a proof of depth k plus 1/2, if it has a proof of depth k plus 1, in which the bottom fan in all formulas is quasi-polynomial in the size of the proof. So if you have small depth bottom fan in, it only counts 1/2 towards the depth. Oh, sorry, did I say it wrong? So I said, yeah, small polylog. I think I said quasi-polynomial. As small, the bottom fan in is polylog in the size of the proof. Yeah. So that's the depth 1/2. And the natural way to go from translations in bounded arithmetic to constant depth is you get these little low depth polylog, these low small size polylog depth bottom fan ends that correspond to sharply bounded quantum. Sorry. Okay. So good. I'm going to finish on time. So great. So that was all I was going to say about bounded arithmetic and constant depth proofs. I just wanted to mention a couple other theorems of Russell's that I didn't cover. The first one was because it uses switching lemmas. This one, Russell and his student Nate Siegerland and myself from 2002. So res k is proofs with depth 1 formulas with bounded fan in at most constant k, or well, not most k is not constant here, is this weak pigeonhole principle that I mentioned before, requires exponential size reputations in res epsilon square root of log n over log n. Okay. And res k plus 1 proofs can exponentially improve over res k proofs for reputations of sets of clauses, right? Sasha Razborov got rid of that square root there. And on the other hand, Tony and Alexei Maciel and Alan Woods showed that the pigeonhole principle is, again, I'm stating their theorem in reverse order here, has proofs in T22 and therefore has polynomial size depth 1/2 proofs, right? They actually did it the other way around. They gave the proofs, correct me if I'm wrong, they gave the low depth half proofs with the, in other words, clauses in which every formula is a conjunction of size and logging, a polylog, right? And then I think after that, Jan or I said, why don't you prove it in pound arithmetic? So they did as well. Okay. So that was the first, so this basically is exact, right? Except maybe some log factors or something like that. Some log factors in the depth. Very, very close. The other result of Russell's is really less related, but I thought might as well throw in something about resolution. They proved Chris Beck and Russell proved a form of strong ETH for regular resolution. Namely, there's unsatisfiable sets of clauses of size k. These are just regular clauses that require regular resolution reputations of size nearly 2 to the n, and the nearly means a constant that tends to 1 as k tends to infinity, right? And this is still open for resolution. And other than that, if I have another minute or two, I'll give some open questions here. Depth D versus depth D plus 1. This is something I've worked on off and on over the years, and I'd say all my own attempts have failed rather spectacularly. The two things I've really worked on most seriously is looking at bounded width. Oops, I'm erasing things instead of highlighting them. Bounded width grid graph ST connectivity principles, which I thought, oh, ST connectivity on a bounded width grid graph is complete for sigma D or for depth D AC0 formulas. So why not use that property to get, well, it didn't work, okay. And then Neil Toppin has an implication principle that Rami and I worked on, and the equivalence version of his implicational principle we were all very happy with, and then discovered that it has polynomial size resolution refutations, certainly not requiring depth D or whatever, right? So the implication principle is still open, but the equivalence principle, which I was astounded to learn, has in fact small resolution representation. So I won't talk about it today, but encourage you to go look up the paper, right? Okay. Other open questions. What about the weak pigeonhole principle in I delta naught? Long-standing open question. If that was shown to have proof in I delta naught, then I delta naught could prove the existence of infinite many primes, I should say arbitrarily large primes. Does it have res order log n proofs of polynomial size? I think that's open. I think so. And then Paris Wilkie did in a follow-up paper, they showed that you could count exactly, take a set of size, take a subset of 2 to the n that has cardinality less than log n to the k for some fixed k, that I delta naught could prove exactly, could exactly define the size of that set. And can that be improved to some bigger numbers? No idea. So thank you. Congratulations. Russell.